So I don't want to repeat this again, but thank you. So we have always a model, right? You can always model any system. Might not be quite accurate, but to some accuracy, and you know, whoever models, they know how did they model, right? You can also use sensors to measure data. To mix them, you just learn, you can use something called Kalman Filter, right? To combine these. But we can't just say, okay, average these two and whatever the number is, we're gonna go with it, right? There should be a system that we can decide how much to trust each of these. So in these scenarios, what do you usually do? I'm not even talking about Kalman filter. Let's say you have two cameras, okay? One looks at a color and says, this is, don't need even a camera, girl, ask a guy what color this is. Blue, green, turquoise, they don't know, right? So you can average that. But let's use two cameras, make it like not human. Two cameras, look at one object and then try to say what color it is. One camera sees it blue, the other says it's turquoise. Then you want to decide what color this is because you're going to do something after. Which camera you're going to trust more? What is the base of your decision?
Run iteration.
He's a businessman. No, because I've paid so much money for things that they didn't work. But the camera usually goes expensive. But why the expensive one is better? What is about it? Why is more expensive? Right. Resolution, higher resolution, right? What do you want to say? Okay. So you're not gonna say throw the other way around because the other one also said blue. It recognized the color, right? The like the spectrum, like around the blue. The second one had a better resolution, more detail. So we're gonna say, okay, based on this experience, 90% of the time, if you say the camera one said blue, we accept, and then the other 10%, you're gonna check what shade of blue it is, right? So you kind of give them base practice or rating. So maybe camera was not a best example, but you get it. I couldn't hold another example I didn't spot. But if you have different sensor, you like, yes. Okay, thank you. Right. So does the weighting part make sense? So you can, so when we say trust something more, you're gonna give more weight to it, right? So same thing, when you're using Kalman filter, you have different data, even data comes from model and the data comes from measurement. We have to know which one we can trust more. Some cases 50-50. We can't trust you 50-50 because I can't make a decision which one is more trustable. For some cases, you're gonna say, hey, I'm using a very good sensor. I'm gonna trust my sensor more. So 80% the sensor, the 20 other percent of estimation is from the model. Now, in terms of coding and using signals, what does this weight factor translate to? Yeah, but let's say you want to code and you want to say, I have two vectors, I'm going to always use 80% from this and 20% from this and combine. What does that translate to? That weight distribution. You have done it.
The weighted average.
Weighted average. Okay. We are gonna see it in Kalman filter. So have that question, right? And you will see the answer very soon. That's what makes Kalman filter, or LQR. The thing that decides how much we trust each of the measurement or estimation. All right, it will come up, don't worry about it. But I want you to think about what I'll explain. So as you said, we have the model of our system. Now for a car is a multi-input, multi-output system, right? Very complicated. We are gonna go from a multi-state to simplified, maybe let's say single state. Let's just look at the position because velocity also affects position, right? Let's say just we look at the position. So our output is gonna only measure our input. It's gonna be just one input gonna give us one output. If our output is y and we have one, so this little bit goes to linear systems if you know how they are formed. So x dot is ax plus b u and y is cx plus du. So you can model any system to a linear system. Now x dot, that's your system itself. So A matrix, for example, mass matrix, right? Is the specification of your system. Y is the output. How my output depends on my input, because you see that there's X, right? So the output can be a function of different input from your multi-input system. So now here our C is 1, so you're only, our output is just position. You're just measuring one of our states. So X is your state. So we estimate, we simplified, for this example, we're going a multi-state system. We have one state, single state, and we are only focusing on position. And we are using the linear system because we're going to use Kalman filter, FK, right? So we can focus on linear system. Now, you have the core dynamics. So you have the model of the system. You know that you might have some process noise. You cannot eliminate that. We're going to say, we're going to introduce process noise, WK, in our state equation. And we're going to introduce a measurement noise, right? Depending on what kind of sensor you're using, you're going to introduce a measurement noise. Now, here is where things get interesting. So, our process noise is random. We can assume random, right? We can use Gaussian. And you'll see that a Gaussian distribution looks like this. Here is your covariance, right? 68% of the time, you're gonna be here around the actual measurement or distributed equally. We are gonna assume Gaussian for our noise as well. Also covariance. So these two tell us how much we can trust. You could have a bell curve or Gaussian that looks like very wide. Or could be very narrow, right? If there are two sensors, let's say, let's encoder. You have two encoders, right? One has a covariance of sigma y, the other has sigma prime. Which one is more trustable? Sigma prime. It tells you that 80%, 68% of the time you're very close to the solution. The other one that's wider, you are still 60% around this, but in a wider range. So this is a better sensor. The more expensive one with a higher resolution, you know, all of those. So your covariance here gonna play. From there, you can decide, I'm gonna, if I had both of these 80% of times, I'm gonna maybe 90% then trust on this one. I can still trust on the other one because, well, depending on the problem, you might actually always end up being around your solution, right? So, this is basically where we have to introduce it to our Kalman filter. So we have to tell our Kalman filter how much we can trust by adding these covariances to our model or to our sense, to our measurement. You might even have two measurements and one model. You might have to have like mix three things together. So you're working with probability. So we then multiply this probability together. It's like, okay, now this is my estimate. I'm gonna be here with this chance. This is the chance that I'm gonna be on this position, for example, for this car, right? So let's check out again, car dynamic. We have A, which is the car specification, mass and damping, well, mass and inertia will show up there. Maybe dampings show up in here. This is your noise. This is your output, which is from your modeling, right? Which is from the dynamic. So that's actual. You can put a sensor. Let's say this reads from a sensor because I have sensor noise. I modeled that car to be this. My model is gonna give me y hat for the output. It's gonna estimate the output is gonna be this much. And the sensor is gonna measure the output, the output that it sees with some noise, and it's gonna throw it away here. So between these, you need to have something to combine. That's where your Kalman filter will show up. The Kalman filter will go between these two, combine the measurement and your prediction from the model, and then finds the optimal estimation. So let's say that your initial estimation from your model was x hat. So when we put hat, this shows estimation. So x hat of k minus 1, the previous step or initial step, is this. So there is a distribution of the position. We don't exactly know where it is, but the estimate is going to be this here, around here. Then you're going to predict the state in the next step. Let's say you 20 meters later, you're going to estimate, and you see that this is getting wider. Your estimate. Why? Some noise happened, right? You went over the speed trap, or, you know, any noise from the environment. But then you measure, your measurement, you see that is more accurate, but you have both of these. Kalman filter will come and combine these two by multiplying it together, and you're going to have something like this. Then this is going to be your x of k for that step. Then you use that as a previous step for your next step until you go somewhere. So this is not you're on one position and keep trying to update the position. There is a dynamic, like the car is moving, there's motion happening here, right? Because if the car was in this position, you get the GPS data, you went from position 0 to here, some odometry, and you have a state. There's no change after that. This happens only when you keep getting data in the system. Does that make sense? So Kalman filter, we use it when we have the motion. And we try to estimate the position as we go. As you go, the position estimation gets better. So it's kind of not training it, but you can adjust your covariances until you get to a acceptable close estimate, for example. All right. Now, how do we create that filter, the Kalman filter? So remember, for example, your controller, you had a control law. For your Kalman filter, you have to have an equation. So your Kalman filter has a gain, right? How do we adjust? Like, what are we adjusting? You're adjusting the gain of Kalman filter. So the equation of Kalman filter looks like this. So look at this first. I should have put this one first. So what is happening here? X, the estimation of your state, right? X is your state. Here is a matrix. This is the estimation of the state in the previous step. So if you start from initial condition, it's whatever it is, initial condition, 0 or whatever number that is, right? So at K1, your X0, you're gonna have a fixed value that you're gonna assume they are correct. So at the beginning, you're in a correct position. As you move, you're introducing error in our motion, right? Then we have B, which is the matrix for how your inputs are applying to your system. So your control can go in here in U. That's also, so that is, you haven't controlled anything yet, right? So that's from the next step after you actually move. So far it's just a linear system, AX plus BU. This part is where Kalman filter comes in. The Kalman filter is K of K, the gain of Kalman filter times YK minus C times AX minus 1 UK. What is this? So let's see what is this, what this term is doing. What is term doing? What's in this parenthesis?
The difference between the actual and the
Yes. So the measurement minus the estimation, right? And whatever error that is, you're gonna apply the gain of Kalman filter to fix, update, or prediction for the next step, right? So if you are familiar with state observers, that's actually the same as equation of a state observer. The Kalman filter is an observer in your system. So sometimes you're measuring everything, you're estimating everything, but you can also have Kalman filter to observe if you're estimating your state correctly. So it's like a just a fact, like a check to make sure that your system is running as it should. We just observe the system, right? And if the estimation was wrong, then we can come in and fix it. So that I shouldn't have this comes from a different lecture. That's why I probably was here. So this equation for any observer you want to use in your algorithm. So if you're using LQR, same thing, same concept happening there. Yes. So linear quadratic regulator. That's another kind of controller, but it uses two covariances. The same thing, kind of like how much impact from one input, how much from the other input to have. So LQR is actually a very unique controller. So usually after PID, if you want to make it more fancy, trying LQR is not a bad idea. And concept-wise, it's simple enough that you're able to implement, like 4-line of code in MATLAB or any other language. Really finding those, I think it's Q and R matrices, the covariant matrices, that's the part of the part that you have to tune. The control law is easy for LQR. So for Kalman filter, we are gonna use the first part and we're calling it a priori estimate. Estimate from the previous round, right? Then you're gonna add the difference between measurement and estimation times the gain, and we can call the new state as a posteriori estimate. So estimation after update still is an estimation. We put hat to show we are still estimating where we're gonna be. So as you can see, the optimal state estimate between this measurement, the predicted state, and the measurement here became something like this. So the car actually is here based on the covariances introduced here. If we had a sensor, if we had a way of saying exactly where the car is, what would happen? This would go where the measurement was. But because both of these are probability, we just multiply the probabilities and say, okay, the car must be between these two. And how do we know how much we trust? Well, the covariances tell us how much we trust each of them, since none of them are exact, right? So Kalman filter is a two-step process. First, you're gonna have some prediction, starting from initial condition or initial state. So for example, if you say K1, so your X had that negative, that is actually, let me explain that. So if you have a negative, that's how we show a priori estimate. We show that this came from estimation of a previous state came from previous state, right? We put a negative up there, so to introduce our a priori. So you use your initial state to find your a priori prediction. So from this state, my prediction is going to be, I'm going to end up here. Then you're going to have to introduce an error covariance, that how much my estimation can have error into it. Now, how do I know this? Where do I get the information? It comes to Q, which if you remember, I think we introduced Q here. Your process noise covariance, right? So what are we doing? So this one is R. So here, because we are predicting from the model, right? So we are using the covariance of the noise introduced to say, hey, my model has this much noise. This is the covariance. So you're gonna say that I'm predicting this, but this with this much error. The error comes from the noise of the model or inaccuracy of the model. That's how you decide about that P value. So we call it PK of a priori is A. A is the system, right? The system times the previous error, whatever it was. If you start from 0, what's your error? 0, there's no error, you just started. Plus, so at first step, there's no error, let's say the initial. No error plus whatever noise this system will introduce to me would be exactly my next covariance error. As you move, this is going to grow, right? If the estimate is not accurate, which would not be. So as you are moving, you are saying that my covariance is going to grow, so the Kalman filter has to compensate for that. So that's basically it. That tells you like, hey, this is going to get wider. You have to tighten it up. That's the step one. So from there, you have XK negative and PK negative. Now you're going to update the stage. This is the important part. You have to find Kalman gain, your a posteriori estimation, right? And then your covariance error. Once you, so these two, you just basically follow this equation. How do we find Kalman filter gain? Depending on C, which is how the inputs, how the state impact the output, we have ABC matrix. And you see here R. Why do we have R in our update? What was R? Do you remember when we checked the sensor, the covariances? The covariance for noise measurement was R. So in our update, because we are comparing the measurement with the state, we have to introduce the covariance of our measurement noise, right? So that happens during the update. So in the prediction, the process noise is applied. In the update, sensor noise. So we're counting for that there. Then once we have our X hat and PK, we go next step, these two go and create our prediction, and then we go back to the update. So keep bouncing between these two until we're done with wherever we wanted to end up with. Now, going back to how much we trust each of them. When you're calculating your state, estimating the state, if you trust both of them the same amount, 50, right? You can, or 50%, if they're not equal, you can change the covariances. Now, if your measurement noise is small, you have a very good sensor, you're gonna trust that more. So you're gonna say that my measurement, my Y covariance is smaller, so I'm going to trust whatever I get from my measurement more. If your model is very accurate, you're going to have the covariance of your estimation a priori. These two show up in Q and R. how you get them. And there are matrices, 3 by 3, 2 by 2, depending on the size of your system. Now, extreme cases, what if our model was exact? What would happen? If your model, if you get the limit of this and put this to, if this goes to 0, so you don't have any error covariance, the result is that x hat and x hat priori are the same. So your model gives the exact value for your prediction. If your sensor is very good, so your measurement covariance is 0, there's no covariance. Every single time when we measure, remember covariance, we are right where we should be. We are not deviating from anything. So covariance is 0. Then look at your state estimation. Is exactly your measurement. So these are the two. Now in between them, you have to change the covariances to trust which side more. That's basically the meat of Kalman filtering. Other than that, the function, the prediction, and the update are simple equations that you already have. So finding out those two covariant matrices are basically your only job when you're tuning for Kalman filtering. You also need to know which state you're estimating, right? So, so prediction, update, prediction, basically that's what you run. You don't need to know all the information about the states at all time. You just need to know what just happened in the past step, in your state, and the covariance error. That's all you need to know. And then you go to next step, and then what you estimated becomes your previous knowledge. So this is good because we can use this for linear system, or if we are linearizing around an operation point, we can just focus on that, right? You don't care what's happening in the bigger picture. So locally, we can move and find operation point and then estimate our state around that. So this is the example that I don't think you have time. I will open it on MATLAB to show you how it is. You have done this, right? You worked on this. We're going to apply Kalman filter to estimate that if the solution we find from the modeling equal to measurement. So now, how do we introduce measurement for this? You can use Simulink and introduce sensors, and that will measure it for you. I'm going to show you, well, I'm going to talk about this because we actually did this before. So when you find the pendulum dynamic without friction, you get to something like this nonlinear term, right? Sine, cosine, and so. Now, this is nonlinear. We cannot use Kalman filter. You have to use DKF. But for smaller value angles of theta, sine of theta is equal to theta. So we're going to linearize this around that operation point, around 0, right? So 5 degrees with -5 and 5, or negative 10 and 10. I think for 10 is still linearized. This is become G over L theta. Now this is linearized. We can use Kalman filter for this. So convert this. So we are only looking at it at a very small operation point. Then coding it, pretty simple from here. You have to use, so this is the part that some of you might not know, but I think for OD you had to do this, right? Linearizing the system. So if that is your system of equation, you're going to create A and B matrix, and your Y, since we are only measuring the position, or theta 1, so C is 1. So A, B, C, D, these are the state representation. A, B, C, D matrix. So we're going to use this in the Simulink model. So instead of using the dynamic like that, we're going to convert it to state space. Now we have 4 matrices that we have seen in our Kalman filter equations, right? All we have to do is what? So we have A, B, C, D. You remember from the predict and update state, what do we need now to define? We need to enter the covariances. write an equation for the error covariance, right, P, and you have everything else. So you could code this in MATLAB, basically, that's what I'm saying. Or you can use Simulink, which is a bit harder. So this example actually does the Simulink. So you have the model for Simulink. I want you to, let's do that. Let's go, let me show you this one so you can, after that, do it by yourself. How to stop the share. Hide here. Start doing it. No. Have anybody, any of you seen Mechanic here before? Okay, so in Simulink, there is a library that you can build things. So that's why I chose this. I wanted to show you that example. So this is the code. I have given you the code. This is where you introduce a parameter. You can change these values. So process noise, you're gonna say that my covariance is gonna be 1 to the power of 10 to the power of -3, sorry. And then this is your covariance for measurement. So we are trusting our process modeling more than our measurement, right? Now, if I can open the Simulink, I opened it, but then it didn't work. Hopefully I can open it here. Just want to show you the sim mechanic part of it. Although if you follow that tutorial video, it will also explain the sim mechanic. So in sim mechanic, you can introduce your revolute joint on top of the pendulum. You can introduce the rod. You can say what's the length, what's the material. And then you can also have a motor, model a motor that will move that joint. So your input is the torque. You can actually create your system. And then you can apply Kalman Filter. Since you're modeling the actual revolute joint and a model of the model of a motor, you can also have a sensor to measure like the encoder. So that's where your measurement comes from. And then your model comes from solving the state of space. Here is your, so if you go here, if you double click on this, you can give initial value, but if you click on here, you can see under this mask, hopefully opens. So this is your system process. This is process noise that's hooked to the motor. Actual data comes from here because this is your model. Oh, right there. So this comes from sim mechanic. You have your revolute joint, you have your link, and then so you have your reference frame that up there. Does not want to move. So connected to this pivot is your reference frame. Torque 1 to this motor is an input. Process noise and input comes from your model. The output is theta. So this is actually measuring this for you. So if you're interested in doing like modeling like this, you can learn sim mechanic. That's another course, but so this is your pendulum model, the torque process noise, and then this is measurement noise. So you're adding some noise to the actual data. So you're faking it, right? So you're kind of faking it. And here is your Kalman filter. If you double click on this, you'll see all of this process in the lecture. You have A, B, C, D matrix, your initial state. Here is your process noise. At the bottom here, you introduce this. So you introduce a diagonal. So only on, so you have covariances on the diagonal. You introduce your R, which is for noise measurement. And then if you run the, going there. So measurement data goes to Kalman filter. U is the state that goes from this here. You estimate your X hat. If I run, I don't know if it will run or not. I think it did already run. You will get an actual what you expect the sine wave. Well, this is the model. It keeps showing upside down because of my frame. But let's say that was fixed. You should be able to see the pendulum moves like that. Probably online working Simulink is not the best idea. Just want to show you the plot. What to expect from it. So when you, that is ran and you're done, you would get, so this is a process how to adjust things. There you go. You get this. So here, estimation is the blue one. We added some noise to our measurement, right? To our estimation to create a fake measurement. And then the green one is, the green one is the actual theta. We added some noise, we created the orange one, and the estimated theta comes from Kalman filter. Now, this is only true around 10 degrees. If you go higher than that, like go 90 degrees, your estimation will be way off. And it's because your system is not linear anymore around 90 degrees or anything larger. Then to solve this, you have to use extended Kalman filter. Thankfully, MATLAB has extended Kalman filter block. You can use the block. Basically, the prediction is a little bit different. The update rates are the update is a little bit different. So you add that block. You have to use Jacobian, and it will give you a good estimate of theta. So we introduce noise, the actual system. You'll see that the calculated, the estimated is not a flat line. It has some noise in it, right? Because the estimation of a nonlinear system. So for nonlinear system, you cannot get exact values. It would be a very good estimation, still not like actual what you expect. So this would be extended Kalman filter. And for that, you need to use Jacobian. And you already know how to create Jacobian, so it should be easy. But you can use values for the Jacobian matrix here if you have the Jacobian of the system. Right? I know this was compact a lot of information, not like a good set out lecture because this belongs to control class, but hopefully give you an idea what Kalman filter does and what's important when you are tuning your Kalman filter. What's important for tuning Kalman filter? To keep the covariances, right? And everything else just following two sets of equation, prediction and update. All right. And you also have to have the model of students. So A, B, C, D, which is the matrices for your system, right? Plus the covariances of how much you can trust your measurement and how much you can trust your model. Hopefully will give you a good estimation of the state that you wanted to estimate. That's all for this semester. Thank you so much. This was a blast. I mean it. I enjoyed and suffered the most throughout 4 years of being honest with you because I had to always be super prepared. So thank you so much for that. And this somehow closed. Oh no. Yes.